Hello, this is the next video on linear transformations. So in the previous video we talked about one-to-one linear transformations, and this time I want to talk about what it means for a linear transformation to be onto. So onto in this case is an adjective. Sometimes it's called surjective linear transformations. So I will say what the word surjective means, or onto, and then explain how to tell if you're given a linear transformation whether it's onto or not. Let's take a look at our generic picture of a function. So you have a set x and you have a set y, and you have a function that's taking the set x to the set y. And let's pretend that x has 3 elements in it. So those are the 3 elements of x, and then y has 2 elements. So remember that y is called the codomain of the function, or it's also called the target. And let's say that my function sends this point to that point, it sends that point to that point, and it sends this point to that point. Well, what's the range or image of this function? It consists of those 2 points, right? These 2 points are, is there a way I can just, no. Those 2 points are the output of the function, and it's the same as the codomain. So when that happens, in this case, the codomain or target is equal to the image of the function f. Or in other words, the image of the set x under the function f. So when this happens, we say that the function f is onto. So we say that f is onto when the codomain is equal to the range or image, same thing, the range of f, or the image of x under f, or it's also called the image of f. It's the same thing. So intuitively what this means, so f is onto when, this is a kind of vague way of saying it, it's when no element of y of the codomain is missed by the function f. That's one way to think about what it means for a function to be onto. Okay. Another way of thinking about it is, some more precise way, is that for every element little y in the codomain, capital Y, the equation f of little x equals y has at least one solution. So in other words, one or more solutions. There's no element of the codomain with no corresponding input. And this is another way of saying the same thing, which is kind of a more typical way in books, is that for every little y in capital Y, there exists at least one x. So there exists an element little x in capital X, such that f of little x is equal to little y. Okay. So let's look at an example of functions from one variable to another variable. So let's say that you have the function f of x. Okay, let's say that we have the function here. I really need to be careful about specifying the domain and codomain. So let's say that I have a function from the real numbers to the real numbers that's given by f of x equals x cubed. Yeah, x cubed. So when you graph the function y equals x cubed, it looks like this. And you can see that every element of the real numbers is obtained as the cube of some real number, and so f is onto. So this function is onto because if you have an element, say little y, in the real numbers, so in the codomain, what value when you plug it into f will give you y? What's the number that when you cube it will give you y? In terms of y, it's the cube root, right? The cube root of y, f of that is equal to y. So that explains why f is onto. Let's give an example of a function that's not onto. So let's say that you have a function from the reals to the reals, which is given by f of x equals x squared. Okay, well the graph is this, right? It's this parabola. This is not onto because what's a value that is not obtained as the square of a real number? If you think of the reals as this target, okay, what numbers are not hit by the function f of x equals x squared? What function is not the square of a real number? The negative numbers, right? The negative numbers are not obtained. If you plug in the real numbers into the function that squares the numbers, you're going to miss all the negative numbers. So it's not onto because there is no x. There's no real number x such that f of x equals -3. Or you could just replace that with any negative number. Okay. Okay. Okay, now that we have an idea of what onto functions are, let's apply this to thinking about what it means for a linear transformation to be onto. Okay, so that's our general discussion of onto functions. Now let's go back to the linear algebra part. So let's say that you have a linear transformation from Rn to Rm. A linear transformation is onto well, let's phrase that in terms of the standard matrix A. It means that AX equals B for every B in Rm. AX equals B has at least one solution. Okay, that's just translating the linear transformations back to the matrices. And do you remember what it means for AX equals B to be always consistent? What has to happen with the pivots? There has to be a pivot in every row. A, or maybe more precisely, the echelon form has a pivot in every row. Or we could say that A has a pivot position in every row. Because, okay, so this is the same as saying that the echelon form of A has no zero rows. And what can we say about the columns of A? They span, remember, AX equals B has a solution when B is in the span of the columns of A. So if every B in Rm, okay, makes AX equals B consistent, that means that Rm must be equal to the span of the columns of A. So the columns of A must span Rm. So all these are different ways of, they're equivalent mathematically to saying that T is onto. Okay, let's just review this fact. Why is it true that AX equals B always having a solution means that A has a pivot in every row? Because so let's say that you have some matrix A, okay, and just imagine you augment it. Let's just do an example. So let's say that the vector B is an element of R3. Okay. Now let's say that when you row reduce this matrix to echelon form, let's say that there's a row of zeros at the bottom. Well, when you row reduce the augmented matrix, this vector B is going to turn into some other vector. And so you're going to get something here, you're going to get something here, and then this number here is going to be in terms of the BIs. It's going to be something in terms of B1 and B2 and B3. And if you have a bottom row of zeros like this, you can always choose the original vector B. You can choose B1, B2, and B3 that makes that number here not zero. So you can choose B1, B2, and B3 that makes to make this non-zero. And if you do that, then you have an inconsistent system. Okay, so in order for AX equals B to always be solvable, you have to, you can't have any zero rows in your echelon form. And that's the same as saying that there's a pivot in every row, because remember, in the echelon form, every row has a pivot row, or it's just the zero row. Right, so if you have a zero row in the echelon form of A, you can make this system inconsistent, right, with no solution. You can choose the vector B to make the system inconsistent. Okay, let's look at some examples. So let's say that you have the function, the transformation T of x1, x2, x3 is equal to x1 plus 2x3 negative x3. Okay, so this is a linear transformation from what space to what space? It's from R3 to R2, right? Because my input vector is in R3, I have 3 components, my output is 2 components, so this is a transformation from R3 to R2. So what are going to be the dimensions of my matrix A? Let's write the standard matrix. It's going to be a what by what matrix? It's a 2 by 3 matrix. Okay, so it's a 2 by 3 matrix. It's going to be like this. And I can fill in, if you just imagine, having like an x1, x2, x3, what do you have to make the numbers to produce the output? You'll see that it's going to be one, 0, 2, 0, 0, 1. Okay. And now this matrix is an echelon form. And does A have a pivot in every row? Yes, right? There's a pivot here, a pivot here. So since A has a pivot has a pivot in every row, T is onto. And let's draw a picture to convince ourselves that that is in fact true, to get an idea of what's going on. So you have the domain R3 and the codomain is R2. And if you plug in the standard basis vectors E1, E2, and E3, those are going to go to 1, 0. See, I look at the columns of A. E1 will go to 1, 0. That's T of E1. E2 will go to 0, 0. That's T of E2. And then T of E3 is 2, 1. So it's going to be this. For E3. So I have these three vectors on the right. One of them is the 0 vector. These vectors clearly span R2, right? Because I have two independent vectors in R2. So since they span R2, every vector in R2 is going to be obtained as an output of the function t. Right, so here's my E1, E2, E3. Do you see what's going on? Any vector in R2 is a linear combination of the columns of A. And that corresponding linear combination, I can take the corresponding linear combination of E1, E2, and E3, and then that vector will go to that vector. So if, for instance, this, if this vector, say, this vector was like A T of E1 plus B T of E2 plus C T of E3, then if I plug in A E1 plus B E2 plus C E3 into my function t, I will get this vector as the result. So that explains why when the columns span the codomain, so in this case the columns span R2, then the function t is onto, because every vector is a linear combination of the columns, and that corresponding linear combination of E1, E2, and E3 will go to that vector. So t will be onto. Okay, let's do another example. So let's say that you have t of x1, x2, x3 equals x1 plus x2, 4x1 plus 4x2. So this is again a transformation from R3 to R2, and so my matrix A is going to be 2 by 3. And what's the matrix going to be? It's going to be 1, 2, 0, 4, 4, 0. Sorry, just copied down my notes wrong. It's 1, 1, 0, 4, 4, 0. And when I row reduce this matrix, I'm going to get this, and so I have one pivot. So I certainly do not have a pivot in every row. Row 2 does not have a pivot. So since A has only one pivot, T is not onto. And let's again try to figure out why this is true from the picture. So T is mapping R3 to R2. And what's happening with the standard basis vectors? E1, E2, E3. Well, they're all going to go, well, E1 and E2 are both going to go to the vector 1, 4. So 1, 4 is here, let's say. That's 1, 4. So that's T of E1, and that's T of E2. And then T of E3 is the origin. And so the image of t, right, that's the span of the vectors t of e1, t of e2, and t of e3, that's going to give me this line. And so what this is saying is that if you take this matrix and plug in all the vectors in R3 and look at the output, what you're going to get is this line. Okay, all of R3 is going to go if you plug in all the vectors in R3 and look at what you get, you only get this line. You don't get all of R2. Okay. So notice that this image is the line. The image of t is the line. All the vectors on this line. And so that goes back to what we were saying about t not being onto means that you miss some of the vectors in the codomain. So what are the vectors that you miss? You miss all the vectors that are not on this line. Right? So these vectors are not linear combinations of the columns of A. Okay, so that's an example of a function that's not onto. We can see it in terms of the matrix. There's no pivot in the second row, and then we can see intuitively, in terms of the picture, what's going on. It's that this function is mapping all of R3 to this line, and so you miss all the vectors that are not on the line, and that explains why t is not onto. Okay. So another way of seeing that t is not onto is to just come up with a vector that is not, just come up with a vector. Like, can you come up with a vector that's not a vector b that makes ax equals b have no solution? It should be pretty easy, right? Take something like 1, 1, or take anything that's not a multiple of 1, 4. And then if you solve ax equals b, you'll see that there's no solution. Okay, so that's a simple way of seeing why t is not onto without thinking about pivots. Okay, let's do a more conceptual problem. So, can a linear transformation t from R2 to R3 be onto? We'll take a minute and see what you think, and we'll go over the answer. All right, let's go over the answer. So the answer is no. Okay. Let's think about this first in terms of the matrix. So the standard matrix of t, so the answer is no. The standard matrix, and the reason is that the standard matrix of t is, so let's call this A. The standard matrix A of t is what by what? It's 3 by 2, right? So when you have a 3 by 2 matrix, okay, how many pivots, what's the maximum number of pivots you can have? 2. So A has at most 2 pivots. And since there are 3 columns, you can't have a pivot in every, since A has 3 rows, A has 2 columns, right? But A has 3 rows, since 3 is more than 2, A has at most 2 pivots, so A cannot have a pivot in every row. So t is not onto. So t is never onto. Now let's think about intuitively the intuition of why this makes sense without thinking about the matrix. Okay. The intuition behind what's going on is that t is mapping R2 to R3 like this. And t being onto means that every vector gets hit. Every vector in R3 gets hit. And what's going on is t Okay, t is determined by where it sends e1 and e2. Right? So t of e1 is going to be some vector like this. And t of e2 is going to be some vector like this. And every vector in R2 is a linear combination of e1 and e2, and it will go to this corresponding linear combination of t of e1 and t of e2. Right? So if this vector is v, this vector is going to be t of v. And so what are you going to get for the image? You're going to get this plane. Right? The image is spanned by getting too many messages. Is spanned by t of e1 and t of e2, the columns of A. And so you're going to get this plane, so there's no way you're going to get all of R3. Right? So t will not, how do I put this in a way that's like precise? Any vector not on the plane spanned by t of e1 and t of e2 is not in the image of t. Right? So t is missing. Just take any vector that's not on the plane, like that vector is not on the plane, right? This if you think about these plane as these vectors, it's just kind of going out of the plane. This vector is not in the image of t. Okay, so that's onto functions or surjective functions. One-to-one functions are sometimes called injective. Now that we've talked about onto, we can talk about invertible. So once we've talked about one-to-one and onto, invertible is easy. Invertible just means one-to-one and onto. So that's the case where you have a function from f to y, and there's a perfect match between the elements of x and the elements of y. So for instance, this point can go to this point can go to that point, and this point can go to that point. So this is an example of what's called a one-to-one correspondence. So we would say that f is invertible. And the inverse, so it has an inverse, which is called, okay, it's written like that, f inverse. And what f inverse does is it takes the y values back to the x values, right? So you just take the elements of the codomain of f and then map them back to the elements of the domain that correspond to it. Okay, so what does that mean in terms of a linear transformation? So again, let's say that you have a linear transformation from Rn. Well, first of all, we've seen before that if you have a linear transformation from Rn to Rm, it's one-to-one. The only way it can be one-to-one is if n is less than or equal to m. Okay, so let's just write this down. So t being one-to-one implies that n must be less than or equal to m. That's something we explained in the video on one-to-one. And t being onto implies that m must be less than or equal to n. Okay, So this is an example with the t being from R2 to R3. In general, if you have n less than m, it cannot be onto for the same reason. So m must be less than or equal to n. And so if t is both of these things, right, if t is invertible, then that's going to imply that m has to equal n, because you need n to be less than or equal to m and m to be less than or equal to n. The only way that can happen is if they're the same number. Okay. And just to be clear, this isn't saying that these conditions are sufficient. I mean, if m equals n, that doesn't mean that t is invertible. Right? So, for instance, if you have the matrix A, where you just have something like this, okay, the first column is 1, 3, and the second column is 4, 12. When you row reduce it, you're going to get this. And so you only have one pivot row and one pivot column. So this function, t of x equals ax, is neither one-to-one nor onto. But let's say that t is, so let's say that you have a linear transformation from Rn to Rn that is onto, that is invertible. So that's the same as being one-to-one and onto. Well, we know that that's the same as A has a pivot in every row and column. But if A has a pivot, if A is a square matrix, so that's a square matrix, n by n matrix. If you have a pivot in every row, then you automatically have a pivot in every column, and vice versa for a square matrix. So this is the same as A has a pivot in every row, and we know that that's the same as saying that t is onto. And if you have a pivot in every row and column, that's equivalent when you have a square matrix to A having a pivot in every column. And remember, that's the same as saying that t is one-to-one. So when you have a linear transformation from Rn to itself, okay, being one-to-one is the same as being onto, and is the same as being invertible. And when A has a pivot in every row and column, what's the reduced row echelon form of A equal to? Just think about what the matrix will look like. It will be the identity matrix. It will be the matrix, in other words, it will be the matrix that has ones on the diagonal and zeros everywhere else. And naturally enough, such a matrix is called invertible. So we'll study this. We'll take a look at how to tell if a matrix is invertible. Well, we actually just gave it away. It's invertible when the echelon form is the identity. The reduced row echelon form is the identity. So an example of invertible matrix will be something like this. If you take the example above and then change the 12 to a 10, when you row reduce it, so the first step is to replace row 2 by row 2 minus 3 row 1, you get this. And then the next step is to divide row 2 by negative 2, that gives you this. And then you replace row 1 by row 1 minus 4, row 2, and you get this. And a quicker way to see that you have an invertible matrix is that you have a pivot in every row and column. And so what does that mean about the transformation? So let's write down the transformation. it maps x1, x2 to x1 plus 4x2, comma 3x1 plus 10x2. So this is an invertible linear transformation, linear map. Okay, that basically wraps up the series of videos on linear transformations. And of course, we'll be talking about this a lot more when we talk about subspaces. Oh, and then maybe one more thing I should add before we stop, so one more comment, is that, you know, linear transformations are not processes that take place over a period of time, right? They just map points in space to other points in space. So sometimes, you know, I've watched these videos where people are talking about linear transformations and they make it sound like it's this process that takes place over time, like it's you know, some transformation happens. That's not what's going on at all. It's just a function. Okay, it's not something that takes place over a period of time. It just maps points in space to other points. And then the other thing to keep in mind that might be useful for thinking about linear transformations is that let's say that you have something like a map from R2 to R2 that's a linear transformation. So let's say it sends E1 and E2 to, I don't know, these vectors. So let's say this is T of E1, that's T of E2. Then if you have the square that's formed by these vectors, that will go to the parallelogram that's formed by these outputs. Okay, because you're looking at the linear combinations where the coefficients are between 0 and 1. And similarly, if you look at, so you can kind of tessellate R2 by these squares, and the corresponding squares will go to the corresponding parallelogram. So for instance, okay, let's call this yellow. This square will map to this parallelogram. And this square will get mapped to this parallelogram. And so on. So that's another way of visualizing linear transformations. Okay. Okay, thanks for watching.